So in this short presentation, I'll try to introduce the proportional controller by means of an example. And the example is an example of a level control. So I have a tank with a liquid inside. I want to control the liquid, so I measure it to use in a feedback loop. I send the measured information to a level controller, and I use this to manipulate through a valve the input flow rate F in U. I will assume that there are some other possibly changing input flow rates that I cannot manipulate, and we'll denote them by F in D. They are, of course, possibly time dependent. And I have an output flow rate here at the bottom of my tank, F out, which I'll assume, because of the fact that it will depend on the pressure at the bottom of the tank, to be proportional to the level or equal to a constant, which I'll denote by C times the level. This leads to the well-known block scheme, where I have a reference for my level here. I measure the level, and I will assume that my sensor is ideal for a second and not included in the loop. This level can be found based on my two inputs. On the one hand, the disturbance, and on the other hand, the manipulated variable. Here is my controller, and the question now is, what do I put inside this block? And this is my error signal epsilon, which is defined as the difference in this case between the reference level and the real level. Okay, well, what can we do? Suppose for a second I have a constant reference, R0, and I have, for now, a constant disturbance D0, or, as you like, F in D0. That's, both are different notations for the same thing. And suppose or assume that at a given moment in time, the level is exactly equal to the desired level. Maybe put the level in red, if that's still possible. Yeah, well, a little bit. Then, of course, we would like the controller to keep the level there. And I think it's clear from the setup in this example that the level will be kept constant at that value only if the total input flow rate equals the total output flow rate, because only in that case the level will remain constant. So if the level is constant and equal to the reference that I have set, then I should make sure that my total input flow rate plus my total equals my output flow rate. But in this case, this is what I'm looking for, the manipulated variable that should be chosen by the controller. This is for now a constant, because I have defined it as a constant over here. And the output flow rate is, in this case, it's equal to CH, but the H is here now constant and equal to R0, at least that's what we hope. And therefore I get that I should have a constant input flow rate, which is defined here. So, in order to keep the level constant, if my chosen reference R0 is reached for a given constant disturbance D0, I should make sure that the controller sends out a constant value for the input, or the manipulated input flow rate. We call this constant value the value that the controller will send out when the error is 0, because that's exactly what we do. We call it the bias and denote it by B. So I repeat that the bias is the thing that the controller should do when the error has become 0 to keep it at 0 for a given reference R0 and a given disturbance D0. Of course, it's possible that the level is not equal to the desired reference R0. For instance, assume that my disturbance input flow rate F in D increases, then the level will start to decreases. Assume it decreases, then my level will start to go down, and I want to bring it back to the desired level R0. Then, of course, I should not just send out the bias, but I should do an extra effort. Now, in this case, we see that reference minus the level here has become bigger than 0. In other words, the error has become positive and is increasing. So what we could do is, instead of just make our controller send out this constant value b, we add an extra term that states that when the error increases, that we take an extra effort to bring back our level to the desired value. In other words, we're going to increase the input flow rate F in U when, for instance, the F in D is decreasing. And the more we see that the level is starting to differ from the reference, the more the error will increase and the more effort the controller should do. So therefore, we add a term that is stating that the effort of the controller is increased when the error itself is increasing. We want to keep things linear, so we do it in a linear way, which leads to the following formula. This Kc is called the control gain. And this is exactly the definition of a P-controller. A P-controller is a controller, in general terms, UT equals Kc, and I will for a second write out the error in terms of the reference and the output signal, which we have called Z before. This P-controller is a controller with two parameters that can be set by the user, such that you have the choice of a constant b, the bias, in order to be able to maintain the desired output once it is reached, and you have another constant Kc, the proportionality factor between the error signal and the manipulated variable, that states that when the error starts to increase, that we increase our control effort. And this, of course, is valid both for the error becoming negative or for the error becoming positive. Now, this is very nice, but of course I have not proven here yet whether this will work. If the height differs because of a changing disturbance, or other possibility, the servo problem, suppose that my reference suddenly changes, for instance to R1, we now have to see what will happen. Does indeed, I should use the red one, does indeed my level will follow the reference at all times if the disturbance or the reference change. But that's for the next presentation. For now, we remember that a P-controller is choosing the manipulated variable in a way that the control effort is increased proportionally with the size of the error, but we also provide a constant value when the that we can use to state that there should be some control at the time that the error becomes 0 in order to keep the output variable at the desired level or output. Okay, that was part 1. In part 2, we'll see what the consequence is for the behavior of the control system.